Okay. So now we're beginning with the second talk, presenting the results for the second challenge, which is the binning challenge. And probably most of you know this here, but just to briefly recap what the problem of binning is, you have in a metagenome sequence sample, you have genomic sequences originating from all the different organisms that are in your sample community. So bacteria, archaea, eukaryota, viruses, all kinds of things. And the task is to basically group those sequences according to ideally the genome that they originate from. Those genomes usually also have a taxonomic label attached. So a bin could either be something like a strain, or it could be as a taxon, or it could be something higher ranking, like for instance a species level bin or a genus level bin, and so on. Right. Why do we need taxonomic binning methods? If you think about it first in a kind of naive way, you might think, well, I sequence a metagenome and then I throw an assembler onto it, and then I will get almost complete genome sequences for all my species in there, all my genomes in there. And this is not the case, as you might have seen from the previous talks, that metagenome assemblers at the moment, they do not allow to recover almost complete genome sequences for various reasons, either for technical reasons or just also because your sequencing depth possibly is not deep enough. So even if an assembler is doing perfect, like the gold standard, there may not be enough data to reconstruct an entire genome sequence. So that's why we would like to group these sequences, either the raw reads or the assembled sequence fragments of varying lengths. And then these groups or bins, they allow you to say something on a genomic level about the individual strains, those genomes, or about everything that comes from one species. So that would be kind of like a pan-genome, maybe, for a taxonomic bin. So ideally, a bin represents an individual genome or a strain. If you cannot do this, for various reasons, you can also resort to using higher ranking taxa as bins. So that's what taxonomic binners do. The binning methods, they group fragments into bins without assigning taxonomic labels. And the taxonomic binning methods, they group fragments into bins, and the bins have a taxonomic label attached. So these are two different subcategories of binning tools. So here's an overview of the binning tools and the taxonomic binning tools that have been participating and included in the binning CAMI challenge. So we have 10 different tools here. There's 5 taxonomic binners and 5 binners. And the tools in italics were added by the CAMI team in collaboration with the developer. So they included those tools into a bio box and then ran them with either default or recommended parameter settings. The other ones are tools where the developer submitted their results in the challenge. And from now, after this, I will be showing anonymized names again. At some point later in this workshop, we can reveal, or either directly later in this workshop or maybe a week or two after, depending on how much progress we make, we can then reveal the mapping between the different things. And for those developers participating here, I know that not everyone knows which anonymized tool is theirs. So what you can do is log onto the CAMI challenge website, and then look under, I think it was user account, look under account, and then you can see basically the name of your tool in the anonymized form. So for those participating in the challenge, if you later on want to kind of see whether you're happy with the way your tool is presented here, then please find out what your submission is called. Okay, so the taxonomic binners. Some questions that are of interest to users are, there's different questions depending on what they want to use a tool for. So it's of interest, for instance, which tools make very precise predictions. So very few false positives among their predictions. This could, for instance, be of interest, well, possibly if it goes into taxonomic profiling output. We will hear about that in the following talk. Some other tools, on the other hand, it might be relevant simply, first, if they have a really high recall. And I was just having a conversation at lunch over this. So if you want to do pathogen detection, for medical purposes, then sometimes it can be really important just to say there's this pathogen in my sample. It doesn't really matter if your bin also has a lot of contamination, but you want to know, yes, this is actually there. And these would be the tools with a high recall. And then a common application is where you want to reconstruct genome bins for these further genome level analysis, and then you would probably like some kind of trade-off. So you would like an okay recall, okay precision. Also of interest is how do non-bacterial sequences affect the results for the different tools. So so far most test data sets only represent bacterial or possibly archaeal data, and we wanted to explore this question to see whether that is something that has to be taken into account. For evaluation, in the CAMI framework at the moment, we included several standard measures. They're commonly used in, I think, in machine learning, and also in the binning field in several publications. And so these are included in the framework right now. So I probably assume that most of you are aware of these different categories. So if you classify individual sequences of distinguishing between two classes, then you can get these 4 possible outcomes. Of the negative class, assignments can be true or false. Of the positive class, assignments can also be true or false. Based on these, you can compute things like the accuracy, how well do you classify the sequences of your overall sample, and measure the precision, which tells you something about the quality of your predictions, how many good ones are among there, the recall, that tells you something about how good a tool is at recovering an existing underlying bin. And then there's derived versions of that, the macro precision or the macro recall or macro accuracy, and these measures are basically averaged over all the bins. So over all the precision averaged over all predicted bins, and the recall averaged over all truly existing bins in your sample. For binners, recently, I think this was suggested to Chris Quince by us, the RAND index or the adjusted RAND index have been used for evaluation, and these kind of as a measure to assess genome recovery. So these allow to assess the degree of overlap if you have for one particular data set 2 different partitionings into groups. And then with the RAND index or adjusted RAND index, you can quantify how large that is. And the taxonomic performance was evaluated for the ranks, for the bins at the different ranks in the taxonomy, so species, genus, family, order, class, phylum, and the domain level. Okay, so first data set and the first results. This is the low complexity data set, and just initially to give you some intuitive impression, 2 assignments, so things that have been assigned correctly to a class, false assignments or unassigned sequences, or sequences that are of unknown origin. And what is shown here is the lowest ranking assignment, whether that is true or false. And here, these are the different tools. Again, some are with different parameter settings, like these 2 guys. And yeah, these are all different tools or versions of tools. So to give you some impression, just visually, this guy, for instance, assigns not too much. And you see that this largest little bar of the assignments is correct species level assignments, for instance. And then above these little red things, these are false assignments at different taxonomic ranks. If you look at it, so obviously it doesn't assign very much, but what it assigns seems to be largely correct, if you intuitively look at that. This guy, on the other hand, assigns really a lot. And if you look at the ratio of this block to this block, it seems that in particular for lower ranks, for the species rank, there's quite a large fraction of false assignments in there as well. So the precision would be low at that rank. And then you have these tools assigning intermediate ranks. These here have a lot of correct assignments, more so than false ones, this guy as well. Which is interesting because it's a different parameter setting in comparison to this tool. And this one seems to be somehow in the medium range. So it has, you see that the blue part here seems to be in relation to false assignments at the higher ranks. It seems to be good. But if you get to the species level, there is more red than light blue stuff. So we can quantify these observations using some different plots. going back, is that clear to everybody or somewhere? Okay. Okay, quantifying this, looking at some more measures. We have here the overall accuracy. How good are tools at assigning individual items over the entire sample? In relation to that, you can look at the macro recall, which is a related measure, but here every bin contributes the same in the performance, not every sequence. So if this measure is higher than the accuracy, that would mean that the tool is better at assigning small bins than large ones. So this is not going to happen, but usually if the accuracy is better than macro recall, then that means the tool is better at assigning things from large classes than from small classes. And then there's the macro precision, which tells you the average precision over all bins, so like this. And then there's a misclassification rate, which tells you of all the predictions, the fraction of false assignments of all predictions. So that would mean, basically that the prediction quality drops, but not averaged over predicted bins. But every item is considered individually. So now, staring at these plots for some time, and looking at different performances, for instance, a lot of tools seem to be doing quite well in terms of the macro precision, so making accurate assignments, if looking at until around the family level at least. So you can see here it's almost 100% for evil yellow 2, and then from order to family it drops to a bit more savvy, maybe around 80%. Or here Fervent Salmon 2 also has a really high macro precision until the family level. This guy as well, this one as well, and also this one. So all the blue boxed ones have a high macro precision. So that means they make reliable predictions until the rank of the family, and then afterwards it drops like for all tools. If we look at the macro recall, then, so this is this green line here, the first thing you can see that actually no tool consistency that has like a really high macro recall for this data set. The two that seem to be doing best are these Prickly Fermi 0, Modest Babbage 5. So these, well, would be the ones to use if you would prefer to get higher recall. But we can't say for any tool that we are in the range of really high recall for this data set. And this is the low complexity data set, so that means that should, in principle, be the easiest data set yet for all the tools. And the macro recall is kind of related to the accuracy, so these tools, this is the red line, and these tools also have good accuracy accordingly. And we have this one here, this Pensive Curie. You can see it is not boxed by anything. It's because the precision is initially high, but then it drops, so it wouldn't be one of the really precise tools. And the accuracy and macro recall, they're also kind of in the middle range, so not quite as high as here. But they're also better than for some of the precise binners, so this macro recall. So this is a tool which is in the medium range in terms of measures. All right, and then if we look at the last measure, the misclassification rate, those tools that make the most assignments here in terms of macro recall and accuracy, what's interesting is that if you go up at the family level, then also the misclassification rate rises. Yes, so it's just an observation. I think maybe this is in agreement with the precision dropping when you move to the lower ranks, and then at some point also the misclassification rate increases. So from that, the lowest ranks are still kind of a problem for most tools, I would be concluding. We still have to look at how the plasmids and viruses affect these results. At least until yesterday evening, I didn't have the plot to show this. But I think from discussing that, all the material, some of these slides were just generated over the weekend. But I think the taxonomic performance for the viral data was not very good for most tools. I think that's what Peter Hoffman told me. Right, so if you move to the next data set, the medium complexity data set, you can first see the same kind of plot here. And in comparison to the low complexity data set, one thing I noticed is that the fraction of the samples assigned decreases further a bit for these tools that assign not too much. So going back here in comparison to this, So there still seems to be a similar picture, so similar trend. You have lots of good assignments and not too many incorrect ones. Lots and lots assigned again for some tools, and these are the same candidates as on the previous slide. If there are no particular questions, whenever you have a question to one of the plots, then please just interrupt me. So if we're moving to these views on macro precision and so on again, we have the high macro precision until family level, again for a couple of tools, and these are also the same candidates as before. We have high macro recall, again for the same candidates as before, and also the overall accuracy correlated with that, and pensive Curie, again with results in the medium range. What's also here, we observe that the precision seems to be quite good here. It's really close to 100% until family level. Here also stoic Albertani, 100% until family level. So I think that's nice. So that says that if you use these tools, you can rely on those predictions until those ranks. High complexity data set. Oh, so any comments on that? Okay. The high complexity data set, so this is the largest data set with around 600 genomes included of many multiple strains of the same species. And the effect now is even stronger. You have little assigned for some of the tools. So here's stoic Albertani, the one of the precise spinners, has been assigned with lots and lots of different versions, submitted with many different versions. They seem to all be performing quite similarly, if I can, looking at this. This one also, these two assign not very much. Then this modest Babbage assigns lots and lots here, not very good predictions. So you have lots of red here at the species level. And this pensive Curie, the one tool with the performance in the medium range. You can see also these different parameter settings seem to perform kind of similarly. Looking at the precision, macro precision recall. The dark blue ones, these seem, so I had different shadings of blue as all these tools, which are the same candidates as before, have good precision, but some were really highly precise. So for these two, you can say that it's precise until genus level almost, and then it drops for the species level really dramatically. Then these two, they also have, but these rather, while the other tools, they seem to be more until family level, and then you start to see the drop. Here, this is also family level, this is family level. And yeah, so these are really precise until family level, and then these start to drop. And then we have the prickly Fermi with the overall best accuracy. I guess it should also get a green box. The macro recall is also higher, so for these two guys, the macro recall is seems also substantially better than for the other tools. And pensive Curie is again in the medium range with the. Okay, so then another question is, how good are taxonomic binners, or can you use taxonomic binners as profilers? So the next talk will be talking about profiling results, and we thought about including some to assess that. And there is no well-established way to do that, to convert individual sequence assignments into a taxonomic profile for a sample. So we came up with this kind of simple approach just very recently, and we will see in this workshop, I don't know if you already have some results, or we will hear in the next talk about it, so we will see how that does. So the idea is this, that we want to, to make an estimate of genome abundance, you use a good way to do so is to take coverage values. And it's easy to do if you do it for marketing reasons or very sensible. If you now have large bins, not just marketing regions, the first idea was to calculate the average coverage for a particular bin or for every bin by summing over the bin coverage times the bin length for every contig, and then dividing by the total length of all contigs in that bin. So that's your average coverage of a bin. And we also include the unassigned bin because we want to consider the entire sequence sample. So everything is either in a bin or unassigned. And then you can simply calculate the relative abundances based on those coverage estimates for every bin as the coverage of that bin divided by all the coverage values for the bins at that rank. And we do this for the lowest rank, so for the species in that sense. And then to go for the ranks bins at higher ranks, you calculate the coverage for a bin as the coverage estimate for a particular bin using that formula, plus the coverage estimate for all child bins of this bin. So these are all genome copies that are added for this particular higher taxon bin in the estimate. And then you can again, based on that, calculate the relative abundance. And yes, and David will show the results. Maybe, well, we'll see. Okay, so now we get to looking at also, this was only the taxon binners, now we get to the binners as well. And the measures that we've been using here were the RAND index and the adjusted RAND index, which gives you a value, a quantification of if you have your data set and you just divide it in different, you partition it in different groups, and then if you compare them, how much does it disagree? If you calculate for the entire data set, which is how Chris Quince who suggested that originally used it, this will give you a measure of bin recovery. So it should be a measure that kind of combines precision and recall in one. What we also calculated is because of the issue that some binners, they don't bin the entire data set, but they leave things unassigned. Then you have a big unassigned bin. And you can, if you now want to not consider that unassigned bin, because you might argue, well, it's not really a true bin, and only calculate it on the subset of data that are assigned to bins, then this would give you, well, for different tools, relative to the standard of truth, they wouldn't really compared on this, they would be compared on different subsets of the data, but it does give you some measure of how good just the set of predictions are, so maybe something like a precision or purity measure. So we calculated this using different references. Once using the partitions into genomes as a reference, and also once using the partitions into different taxon bins as a reference at a particular rank. But this we so far only have for the taxonomic binners. Okay, so here's for the low complexity data set, a comparison of genome bin recovery. And included in here are the unsupervised binners, so the binners, but also the taxon binners. So we thought, as a biologist or applied user, if you want to get at genomes, if you want to recover genomes, you might use a taxonomic binner, and you don't really, to you it doesn't really matter whether the taxonomic binner actually just assigns species because of limitations of the taxonomy and doesn't allow to resolve below strains. So we thought it was just interesting to include that as well. And so this is a standard of truth. It has an adjusted RAND index of 1. And I just put some bars in here to make evident which ones seem to have the best genome recovery values. So actually it's these two, Berserk Pasha and Norty Carson. But there are several others of the unsupervised binners. I mean, they all seem to be performing not so much worse than, so in the medium range, I would say, which is encouraging. There's nothing that goes down that doesn't work at all. The guys down here, these are the taxon binners. So you may not want to use these precise binners for genome recovery is the solution, the conclusion of that, even though this one setting has a, well, performs like only slightly worse than the binners. And this is now the computation of the purity, so just looking at the predicted subset or the group subset of the data. And we have Nordic Carson 2 as a very precise binner. Was that the same? Yes. So it's also one of the better performing tools, and it has also, the predictions are really precise. And then we have, there's another one which has precise predictions, so which is one of the supervised taxonomic binners, so which is one of the precise supervised taxonomic binners. So I guess that explains also this observation. And then you have here these different categories with all the unsupervised binners again being here in the medium range in terms of purity, the remaining unsupervised binners. Does that make sense? Or any questions? Okay, do you know by now, does anybody know whose tool is which one, or is it still unclear? c'est unclear. Okay. We did the same comparing versus taxon bins, and so this is always this RAND index, but now just to seeing how the purity is with bins at different taxonomic ranks. And you can see for some of the precise tools that this really agrees also well. They also have high ARI. Yes, and I think maybe it could be nice to include also the unsupervised binners in that, so we see how well a unsupervised binners could be at recovering, for instance, genus level bins. For the medium complexity data set, these are the results here. We have again the gold standard, and up to here, these are the unsupervised binners. And you can see that now three tools have seem to be performing similarly and best in genome recovery. And you also see that the index is slightly lower in comparison to the low complexity data set, which I think makes sense since the data set gets more complex. And of the supervised binners, we have one tool which seems to be doing okay in genome bin recovery. In terms of precision, we have this Norty Carson again, which is doing very well in terms of precision, and one of the precise taxonomic binners, and the other ones being kind of in a medium range, whereas most taxon binners are not very precise genome reconstruction tools. Interestingly here, if you look at taxon bin purity for this data set, it seems to be better for the lower ranks than for the low complexity data sets for some of the tools. I found this a bit surprising, but maybe we can look into that. And this is the last data set, the high complexity data set, again the standard of truth, and now you can see how the genome reconstruction really drops. We have 600 genomes in there, and the best performing tools, they have, here they have an ARI of 0.45, two of them, and most other tools though, it really drops dramatically. And so there's a further performance drop in comparison to the medium complexity data set. And these results kind of agree with what's been seen before on terms of which tools are really give good purity on the groupings. And here we now again have some tools that have really precise bins or pure bins, whereas some others drop at the species level. So below family level, again, we see a bit less good performance. So what's still to be done is to visualize how performance differs for low abundant genomes or species, bringing some data together, which you can do at this workshop. And some indications you can see by comparing the macro accuracy or the macro recall to the overall accuracy, but having some nice overview plots probably would also help. With that, I come to an end. So I think you've seen already the many people that have participated. These are mostly the ones participating with early concepts and providing data. Of course, we also have the tool developers, which aren't included all on this slide yet. And this is a picture of our core team 2 years ago. In fall, it was actually here at ENI also, at our first hackathon. So I think, well, many people are here today from that meeting. And in particular, as the data that I've shown was, I think a lot of it was generated over this weekend. And the two people who've been working a lot on this were Peter Baumann and Peter Hoffmann, whom I would like to thank particularly for that, for investing the hard work. And I also want to thank the developers that contributed with evaluation measures, so Ivan Gregor, Johannes Tröge, Ruben Garrido-Otter. He generated some of the nice plots here. He unfortunately is ill and cannot join us today, therefore, so that was unexpected turn of events. And Ike Dams, who also contributed to putting binning tools in Dockers. So with that, I would like to finish. Yes?
Sorry, I'm still a little bit confused about the metrics. So for every binning tool, you have 2 slides. The first one shows maybe say overall precision or overall range.
Which, should I go back to the slide?
Later. later.
Oh, sorry.
Yeah, later. So, for example, this one shows, maybe say this one shows some metrics. I'm guessing this is adjusted rand index.
Yes.
And so say,
Kind of hard to
for
read.
example, this one, and could you please go to the high complexity? Yeah. Okay, high complexity. For example, Nordic Carson here shows 0.01 adjusted rand index, and for the next slide, Nordic Carson actually ranked the highest. So
Yes.
I feel like there's some discrepancies in that, and I probably don't get something.
Yes, sorry. So this is these are the two different ways of computing the ARI.
Yeah.
So here. So if you compute the ARI for the entire data set, then this is what's shown on the first index, which is what I call the genome or bin recovery measure. So the entire data set. If you only compute the ARI for the subset of the data that was grouped into bins, a large part might be unassigned, then this is what's shown on the second slide. So what that means is that Nordic Carson actually assigns, well, probably it doesn't assign very much of the data for this data set. But what it does assign, it does with high precision, so very good predictions.
I understand. Thank you very much.
Yeah. So I think we have to distill some general conclusions out of this. So what are the most interesting things? What are the key trends we can take out of that? And we can discuss at this workshop what we think these are. I think so. One of them is what we discussed yesterday, that most tools perform well in terms of precision until the family level. So that seems to be something. And that below, it's it drops. We go to the detailed values. So below that, bins are still not really so trustworthy in terms of their content. So they contain a substantial amounts of false positives also, and people should probably be aware of that. Yeah.
So one of the reasons why is that the number of replicates are limited, considering the number of genomes in there. Like the high complexity is the 5 samples, right? So
you mean
one of the next? I mean, it's not covered in the first CAMI challenges, but but next challenge may be interested to consider the number of more samples.
Absolutely,
The effect
yes.
of the number of samples to the community, and then it resolve the the low precisions in the low rank.
Yes, yes. So you mean for the binners that use the multi-sample binners, they would be much better if you wouldn't have had 5 samples, but if you would have 50 or so.
Yeah, 50
Yes.
samples would be better to
Yeah.
To separate those species.
Yes. Yes, I think that's an important point for this discussion, that we have to say this is really relevant for people with a budget that can do up to 5 samples, but for really large-scale projects. But yeah, we should discuss in particular for future CAMI challenges how we want to make new data sets look like.
When we reveal the names, it should actually become obvious I think in the medium complexity data set. Right? Because for the medium complexity, we shifted the community by pretty much, right? Here for the high complexity, it's just this time series where it changes a little bit, but not that dramatically, I think. But maybe the tools still need 50 or 100 samples to work very well. But at least for the medium data set, there's a real shift in the community where basically everything shifts around. So that should be. We should actually see if the effect here in the medium complexity data set.
So things that do well here, but not where you say the effect is in part not just due to the one sample being more complex, but also because the differential abundance is more informative here.
Yeah, that's
Yeah.
right. Yes.
Yeah. So.
But I think you're right. We should generate another data set with I don't know, 50 samples.
Yeah. I mean, the thing is, we have two measures here on which we evaluate the binding tool. So we have the rand index on the entire data set and rand index on the subset of the data. So it's not that many dimensions that we're looking at the moment. Yes. Is there anything else we should look at in terms of measures for the binners, or is that okay? Are you happy with using the rand index or adjusted rand index for performance assessment?
The question is, how many of us here is familiar with the adjusted rand index?
Yeah. So who is anyone? I don't know. And we discussed this at this workshop last year, and I think people then said it's an okay measure, but if you have suggestions and other things to use, it might also be interesting for future challenges. Are there other things that you have been using? I think the mutual information was also one thing to look, but it's similar to these measures, so it doesn't really give you much different.
F-score is also similar to this one, so.
Yeah, isn't there a problem with calculating that though? Because you have to match the partitions onto each other somehow, and you have to know which one to compare to which other one.
Yeah, sometimes it's.
But you could do it probably, kind of.
For the ANI, you consider each content in the same way, right? Like the larger contents, maybe it's more like you can apply some weighted rates. Larger content has more weight.
Yeah.
It's weighted.
Is this weighted?
Yes.
Yes.
So it's based on the confusion matrix, basically, which is weighted by base pairs. So it's you could think about calculating it in an unweighted way, but I find it more useful to
Yeah,
weight it.
really more.
Okay. Right. More questions? Okay. Well then, thanks, and I will hand over to the next speaker. We have 4 minutes until the next talk. If you want to make a brief break.